Right, welcome back everyone. Unfortunately we had to break in the middle of a calculation last time. That's what I try to avoid, but sometimes I do not succeed. So we are calculating the radiation from a binary. Yeah? Two stars orbiting each other, and we want to calculate the radiation, the gravitational radiation which comes from this system. I said that we assume that the motion can be described in Newtonian terms. Of course, not the radiation. This is a genuinely general relativistic phenomenon. Yeah? But for the motion, we assume it's a possible approximation to consider this motion as Newtonian. And what we need for that, there's one thing which I said, that it's necessary that the distance between the two stars is big in comparison to their Schwarzschild radii. What I forgot to say is that it's also necessary that the distance is big in comparison to the physical radii. Yeah? So if the two things are very close together, that the surfaces almost touch, then of course we would have strong tidal deformations and things like that, which would this mass point approximation render more or less meaningless. But both approximations are to a very good degree satisfied by binary pulsars like the Hals-Taylor pulsar. So I said already, the distance is more than a solar radius. So and the Schwarzschild radii, they are stars. Yeah? So the Schwarzschild radii is not very much different from that of the Sun, something like 3, 4, or maybe 5 kilometers. And the physical radius of a neutron star is something between 10 and 20 kilometers, which is also very small in comparison to the solar radius. So these assumptions are really satisfied for the case we have in mind. Okay, and what we wanted to calculate was we wanted to apply Einstein's quadrupole formula. For that, we needed these awful third derivatives of the quadrupole tensor, and I got stuck in the middle of calculating them. We had a quantity I1, was a scalar quantity which determines the quadrupole tensor, and I calculated the third time derivative on the board. And what we got was m1, m2 are the masses, epsilon is the eccentricity of the Kepler ellipse, phi is the azimuthal angle, phi dot, its time derivative, and A1 minus epsilon square A is the semi-major axis. And then I just gave you the result of the third time derivative of this quantity. I typed it out in the lecture notes, but I didn't calculate it on the board. So the result is 2g m1 m2 over A 1 minus epsilon squared e to the 2i phi dot minus epsilon sine phi minus 4i 1 plus epsilon cosine phi. Okay, that's it. And these quantities are needed for this product which enters into the quadrupole formula. This was a trace-free quadrupole moment, third derivative, transvected with itself. That's the quantity we need for Einstein's quadrupole formula. And I had shown you last time that this is given by these two expressions. 1 over 6 I1 triple dot squared. So this thing gives us the first term, and then 1/2 absolute value of I1 e to the 2i phi triple dot squared. So that's the reason why we calculated these two expressions, right? Because they give us this expression, which is the one we actually want to know. Okay, and now we have to, to conclude the calculation, inserting these expressions here, and then we need the time average of this. So that's the calculation we still have to do today. It will take, I don't know, 15 or 20 minutes, and then we have the radiated energy. So let me insert this. 1, 6. So I have to square this here. Then the minus sign goes away. I have a 4g squared, m1 squared, m2 squared, epsilon squared, sine squared phi dot squared, divided by a squared 1 minus epsilon squared. And then I have to take the modulus of this here and square this with a factor 1/2. Yeah. Okay, this is real, so I just square it. 4g squared m1 squared m2 squared a squared 1 minus epsilon squared squared. This is of modulus 1. So the square gives just a factor of 1. This is phi dot squared. And this is a complex number. So the modulus squared is real part squared plus imaginary part squared. So this is epsilon squared sine squared phi plus 16 1 plus epsilon cosine phi squared. Okay, that's it. Well, you see there's a common factor, so it can be a bit simplified. This gives a 2/3, right? 2/3. So let me take this term out of the bracket. Then I have 2/3 g squared m1 squared m2 squared, and also the phi dot squared. It's also in both terms, right? Phi dot squared divided by a squared 1 minus epsilon squared squared. And then I have, from the first term, I have only this here, epsilon squared sine squared phi. And here I have a factor 2/3 written in front of the bracket. So here I have a factor 1/2. So I have to multiply this with, wait a minute. No, I have a factor 2. I have a factor 2. So I have to multiply this with 3. Right? Inside the bracket, I have to multiply it with 3. Then I get a 3/2. So plus 3 epsilon squared sine squared phi. 3 times 16 is 48? I think so. 1 plus epsilon cosine phi squared. Okay? So now we want to time average this. Time averaging means integration over time and then dividing by the time interval. Integration over time. If I had only one factor phi dot, this would be very nice, because then I could integrate it very easily over dt. Yeah? Unfortunately, I have two factors. So I express one of the two factors by an expression we had last time on the board. So I write 2/3. Here I have a common factor 4, right? This gives 4 epsilon squared sine squared phi, and 48 is also divisible by 4. So let me take a 4 out of this curly bracket. Then I have 8/3 g squared m1 squared m2 squared, and I write only one factor phi dot, and the other one I express a squared 1 minus epsilon squared squared, and here I write phi dot in a form we had last time on the board. We had last time seen that phi dot was this here, root g m1 plus m2, 1 plus epsilon cosine phi squared divided by root a cubed 1 minus epsilon square cubed. And this here is phi dot. We had derived this last time. Yeah, we had expressed phi dot in terms of the angular momentum, and then we had integrated over a whole period, and this gave us an expression for L dot, and then we got this here. And then there's a curly bracket. I have taken a factor 4 out, so I have now epsilon squared sine squared phi. 48 divided by 4 is 12, right? 12, 1 plus cosine, epsilon cosine phi squared. Okay. That's it. And here I think we can simplify this a little bit. Okay, let me write a new line. So this is 8/3. I have here a g squared. This is g to the 4/2, and 1/2 is 5/2. Then I have m1 squared, m2 squared. The phi dot I write in the end. Here I have root of m1 plus m2. And here I have a 4/2 plus 3/2 is 7/2, right? When you deal with gravitational waves, such funny powers occur quite frequently. And here I have a 3/2 plus 4/2 is again 7/2. 7/2, okay. And then I have the cosine terms, 1 plus epsilon cosine phi squared. And because all the other terms are expressed in terms of cosine, I also write the sine squared in terms of cosine. So then it becomes epsilon squared minus epsilon squared cosine squared phi, right? Plus 12, 1 plus epsilon cosine phi squared phi dot. Okay, and this I have to average. Yeah, for the quadrupole formula, I need the time average of this thing. Okay, this has nothing to do with averaging. It's just a constant factor. 3 to the 5/2 m1 squared m2 squared root m1 plus m2 divided by a to the 7/2 1 minus epsilon squared to the 7/2. And what does averaging mean? Averaging means divide by a period and integrate over time. Integrate the time variable over a full period. Yeah? This process, this is what we denote by this pointed bracket, time averaging. 1 plus epsilon cosine phi squared epsilon squared minus epsilon squared cosine squared phi plus 12 1 plus epsilon cosine phi squared. And now you see phi dot is d phi by dt. And I integrate over t. And you see this can be nicely calculated, right? So this makes me the t integral into a phi integral, which goes from 0 to pi. That's the reason why I left one of the two factors phi dot, because it was very useful. But I expressed the other one, which would not have been useful. Okay, and now I have to, oh my goodness, I have to multiply this out. So you see it gives terms with powers of cosine of phi. Yeah? And well, I write this first as a phi integral. 8 g phi half m1 squared m2 squared root m1 plus m2 divided by a to the 7/2 1 minus epsilon square to the 7/2. Well, and t can be expressed with the help of Kepler's third law. Yeah. So t is what was it? 2 pi a to the 3/2 divided by root g m1 plus m2. Yeah, this here is 1 over t. If you solve for t squared over a cubed, then you have the familiar form, right? I have just here solved for 1 over t. And now I have an integral over phi, so it goes from 0 to 2 pi. And yeah, I have all this rubbish. Okay, let me write it first, and then we talk about what to do with this integral. Epsilon squared minus epsilon squared cosine squared phi plus 12 1 plus epsilon cosine squared d phi. So you see, if I multiply this out, I get powers of cosine of phi. If I have an odd power, to the power 3 or to the power 1, these are terms which occur, and I integrate over a full period, this gives 0. Yeah? An odd power of cosine integrated over a full period gives 0. But the even powers do not give 0, so I have to collect only the even powers. And that's what I do now. Oops. So, well, what can I do with the prefactor? A little bit. Let me see. This gives 4 over 3, right? Here I have 2. G to the 5 half times root g gives g to the 6 half, that's g cubed. M1 squared, M2 squared. Root M1 plus M2 squared. So this gives M1 plus M2. And in the denominator I have a to the 10 half. This is a to the 5. And 1 minus epsilon to the 7 half. Epsilon squared to the 7 half. And there is a pi. I think I have everything else. Pi. Oops. Okay, and now let's collect the cosine terms. Integral from 0 to 2 pi. So if I multiply this out, I multiply with 1 everything here, and I drop the odd terms because they give 0. So then I get an epsilon squared minus epsilon squared cosine squared phi. And when I multiply the bracket out, then the mixed term gives something odd, which I don't write down. So this gives plus 12 epsilon squared cosine squared. Okay, that's what comes out if I multiply the curly bracket with this one. Then I get a mixed term, 2 epsilon cosine phi. This gives, if I multiply 2 epsilon cosine phi with this, I get something odd for the square terms, but not for the mixed term. The mixed term gives something. This gives 24 epsilon cosine phi times 24, another epsilon, another cosine. And then the last term, when I have epsilon squared cosine squared phi multiplied with this, then I get plus epsilon. So I have to multiply this with cosine squared phi epsilon squared, right? So this gives an epsilon 4 cosine squared phi minus epsilon 4 cosine to the 4 phi plus 12 epsilon squared cosine squared phi plus 12 epsilon to the 4 cosine to the 4 phi. I guess that's it. And now I collect powers of epsilon, of course. Of cosine phi. So I have 4/3 g cubed m1 squared m2 squared m1 plus m2 a to the 5 1 minus epsilon squared 7 half 1 over pi. Okay. Let's see. Terms without cosine phi. I have a 12 plus epsilon squared. Then terms with cosine squared. Okay, I have minus epsilon squared plus 48. Is that true? That's minus 47. Minus 47. No, nonsense. Plus 47. Plus 47. Plus. Oh my goodness. I write it out. That's too hard for me. It's minus epsilon squared. Then here plus 12 epsilon squared plus 48 epsilon squared plus epsilon to the 4 plus 12 epsilon squared. And then I have the terms with cosine to the 4. No fourth power here. Minus epsilon to the 4 plus 12 epsilon to the 4. Oops. d phi. So let's see what I have in the square brackets. 12 plus 12 is 24. That's 72, 71. 71 epsilon squared, and then this term plus epsilon to the 4, and that's it. Oops. So now I can integrate this. M1 plus M2 divided by a to the 5, 1 minus epsilon squared, 7/2, 1 over pi, bracket. Okay, 12 plus epsilon squared, integral 0 to pi d phi, okay? Then this term here, plus 71 epsilon squared plus epsilon to the 4, integral 0 to pi cosine squared phi d phi. And the last one, plus, is that true? Yes, I think it is true. 11 epsilon to the 4, integral cosine 4 phi d phi 0 to pi. Okay, I think everybody can solve this integral. It's of course 2 pi. Who knows what this integral is? We had it already. Pi, exactly. Does anybody know what that is? I don't. I had to look it up. It's 3/4 times pi. Yeah, I think you can calculate it yourself with a partial integration. Yeah, and then you use trigonometric identities. You express sine by cosine and the other way around, and that you could figure it out for yourself. But that's not necessary. You can just look it up. And now we have our final result. M1 plus M2 divided by a to the 5, 1 minus epsilon squared, 7/2. Okay, let me write this out. 1 pi. This is, how do I write? Yes, 24 pi plus 2 pi epsilon squared. Then 71 epsilon squared is epsilon to the 4 times pi, plus that's 33 over 4, right? Epsilon to the 4 pi. Okay, the factors of pi go away. And then I have terms with epsilon squared and terms with epsilon to the 4, and that's our final result. I think I can write it here. 4/3 G3 M1 squared M2 squared M1 plus M2 divided by a to the 5, 1 minus epsilon squared, 7/2. Okay, let me take this 24 out of this bracket so that that I get something 1 plus a rest. 4 times 24 is 96. Yes, 80 and 16. Then I have a 1 here, which is nice. And I have 71 divided by 24. 71 divided by 24, which looks odd. No, wait a minute, I forgot something. 73, right? 73. Which looks odd. Usually if you get factors of this kind, you start suspecting that you might have made a mistake, but this factor is true. It's really there. And here I have 33 plus 1, 34. Oh, 34, that's 17 divided by 2. 17 divided by 48, is that true? 48 epsilon 4. Let me check. No, 37 divided by 24. No, here, I'm in the wrong line, sorry. 37 divided by 96. Oh, how is that coming about?
That's right.
Yeah. Wait a minute. Let me do it slowly. So here I have 1. If I put this on a common denominator, then it becomes a 4, right? 4 divided by 4. 4 plus 33 is 37. And then I have a 4 in the denominator. 4 times 24 is 96. Okay, that's it. And that's the correct result. So this is the time average. That's what we have calculated, the time average of this product. And this gives us the radiated power. I hope everybody remembers the quadrupole formula, which gave us a power at time t going through a sphere, a big sphere of radius r. That's what this formula does for us. This was, what was 5g over, no, g over 5 to the c to the 5 times this average. So I have to multiply this term with g divided by 5 c to the 5. So then I have 96. There's another 5, so I have a 15 here. I think this can be simplified. I can divide by 3, right? This is 32 by 5. 32 divided by 5. Is that true? Let me check. I didn't divide it out. Uh, 32 by 5, yes. Then I have another factor of g, so it becomes a g to the 4, c to the 5 here. And then the rest I just copy from there. m1 squared, m2 squared, m1 plus m2, a to the 5, 1 minus epsilon squared, 7/2, times 1 plus 73/24 epsilon squared, plus 37 divided by 96 epsilon 4. Really funny. So this formula was found by P.C. Peters in 1964, one of the most important papers on gravitational waves. And yeah, we can look at it and discuss it a little bit. So G4, G to the 4 divided by C to the 5. This is in conventional units. That's a tiny number. Yeah? C is very big. G is comparatively small. So the whole thing is tiny in conventional units. So if you want to get something measurable, then the rest must be really big. So M1 and M2 must be big. So it works not with pebble stones. It works with stars, with celestial bodies. Yeah, we need big masses. And A even comes with a power of 5 in the denominator. So the things must be close together. This has a strong effect. Yeah, if they are far apart, the radiated power will be very small. So we need compact objects, yeah, close together and very heavy. Then it works. And there are two kinds of candidates in the universe. We are fairly convinced that they really exist. These are neutron stars and these are black holes. Yeah? Neutron stars and black holes, they make promising candidates for producing gravitational waves by this process. Ordinary stars, we can forget about them, yeah? Because they cannot come close to, sufficiently close together. Yeah? This factor is in the way. You also see that the eccentricity is not very important, yeah, unless it is really extreme. Yeah, if it is very, very close to 1, then this would give an important contribution. But, well, for ordinary binaries, yeah, this is not very close to 1. And then this is of the order of 1, and this is also of the order of 1. Yeah, it doesn't give factors of 10 to the 7 or 10 to the 8 or something like that. Yeah, so this has no strong effect on the order of magnitude. So the masses are important. We need big masses, and the distance is important. We need close a closed pair of binaries. Okay, now we have calculated there is this radiation. Einstein's quadrupole formula tells us there is this radiation. Now the question is, where does this radiation coming from? So if energy is radiated away, then it must come from somewhere. Recall, we have a conservation law, right? This is, you have proven this in one of the tutorials. In the formalism we are using here, which is an approximative formalism, we have this conservation law with a partial derivative. So it's really a true conservation law which can be integrated over. This is 0. So the whole thing together, here's a matter energy momentum tensor plus a pseudo tensor which comes from the gravitational field. The two things together give something which is conserved, give an energy which is conserved. Now we have calculated this radiation which comes from this term. This term produces an energy flux through this surface. Where is this flux coming from? Yeah? Something inside this big sphere must produce this flux, and the only candidate for this is a matter energy momentum tensor. So the sources must lose energy. So unless somebody is pumping in energy from the outside, the system will lose energy, so it cannot be time independent, as we have assumed throughout this calculation. Yeah? So the orbit cannot be time in. The orbital parameters cannot be constant. Yeah? And so the energy must be a function of time in order to produce this radiation, and then we can explain where this energy comes from. Otherwise, we have no explanation for this energy. When we did the last worksheet, when we considered, for instance, the mass, which is oscillating up and down, I said, think of an external driving force. Yeah? Somebody is moving this force. And then, of course, radiation go away without the system losing energy, because you are pumping energy into the system. Yeah? Then the conservation law can hold. But nobody is pumping energy into a binary system. I've never done this. Yeah? I think neither have you. Yeah? So the energy in this system is just the system is left by itself. And so the only thing it can do is to lose energy. And we now want to calculate the amount of this energy from this formula. So this radiated power will be equated to an energy loss, dE by dt, where E is the energy of the binary. And this will tell us how the parameters of the system change, in particular the semi-major axis. Yeah, so what will come out, and I think that's what you expect, is that the semi-major axis decreases in the course of time. Yeah? And the period increases the frequency increases in the course of time. Yeah, so the system becomes closer and faster. And in this way it can produce the energy which is radiated away. So we...
May I ask a question?
Sure.
So, but does this really mean, when they become closer, that the energy is lost? How can you tell it?
Well, the argument why I'm saying that energy is lost is this here. It comes from this equation. Okay. Yeah, and then I have to ask myself, where is this energy coming from? And the only idea I have is that it comes from the motion of the system. Yeah, the mechanical energy of this system is decreasing in the course of time. Or do we have another idea? Where else should it come from? Yeah.
Yeah. So the velocity becomes smaller than all.
The velocity, if you mean the angular velocity, this becomes bigger actually. Yeah, because they come closer together. Yeah. So at first sight, this might sound contradictory. Yeah? Although the energy becomes smaller, the things become faster. Yeah, but they are closer together. Yeah, and for this reason it fits together. Okay, we will calculate the energy now. Then.
Can I also just have on this eccentricity? I think, like, if it goes to 1, you would also have like kind of a parabola. So maybe also the integration over the whole period would be very long.
Yeah, I'm not sure if this could be understood. Chris asked about the limit epsilon to 1. If this is an allowed limit, well, epsilon equal to 1 is not allowed. But I can come arbitrarily close to 1, then I still have an ellipse. Yeah? So in principle, I can have, where's the term? Here. This term here. In principle, it could be arbitrarily small. Yeah? I could have, theoretically, I could have a binary where epsilon is 0.9999999. Yeah? So binaries of this kind are very rare, if they exist at all. But theoretically, you could think of something like that. And then this term could give a considerable contribution. But that's a theoretical possibility, which is probably not relevant for any system in nature.
I thought that maybe then it's considerably large enough, but I mean you still have to integrate over the time period, and that should take some time because you're very, very eccentric, right? Or does that?
Yeah.
Is that not important?
So the question is about this integral here. If the ellipse becomes very eccentric, then the t, of course, becomes very big. But as long as it is finite, the integral is still a mathematically well-defined thing. Yeah.
About if you can measure it, then if you could really measure it, then because you have such a big time.
Okay, you think you have to wait longer than the age of the universe until the thing made one revolution? Of course, then we are out of the domain of application of this. So here we are thinking. Well, we will talk about the Hals-Taylor pulsar, about the parameters. So this thing has a period of something like 7 hours or so. Yeah. So in 7 hours, there's a full revolution done. And so these times are really short in comparison to times over which we can make measurements. Yeah.
But for instance, if epsilon is really equal to 1, it's a
then it's no longer an ellipse. This is not allowed. Yeah, this is not allowed. Then the t would not be finite. Yeah. So this case is excluded. So epsilon is in the open interval. No, it can be 0, but it must be strictly smaller than 1.
Okay, but if it is 1, then we are not going to have any gravitational waves, or?
Well, this calculation simply doesn't apply because we have assumed we have here a motion over which we can perform this average. Such an average then simply doesn't exist. Yeah. So we cannot apply this whole mathematical. Okay, what should I leave? The formula for P. Where's P? Here. This I should leave. Okay, so from this formula, we conclude binary system. I think one uses the plural here. Or no, a binary is singular. These are the 2 stars, right? A binary is something which consists of 2 stars, so it's a singular. Binary loses energy, so we have a formula of the form. This P of TFR, what we have calculated here, must be minus dE by dt. And because it arrives at the retarded time, it will be something of this kind, right? Because always the signals have to travel with the speed of light. And this we have to calculate now. This we have to calculate. We need to know how it is related, in particular to the semi-major axis, and then we can find out from this equality how the semi-major axis changes. So the energy of the binary. Well, we had this almost on the board. What we had on the board was a Lagrangian. The Lagrangian is kinetic minus potential energy. So we just have to change the sign for the potential energy in front of the potential energy term, and then we get the kinetic energy, right? If you look at the Lagrangian in your notes, or in the lecture notes I have sent around, then you will see the kinetic energy term was m1, where am I here? m1, m2 divided by 2, m1 plus m2. This is the reduced mass, right? Times r12 dot squared. R12 was this relative coordinate, yeah, the distance between the two stars, plus r12 squared phi dot squared. Yeah, that's the kinetic energy. And then we had in the Lagrangian with a plus sign, and now with a minus sign, the potential energy. R12, of course, yeah. Okay, we can, with this term we can do something. We have an expression, we have already used it today for the phi dot. I leave this as it is, plus r1 squared. Or we also have an expression for r1 squared. Here we have the formula for the Kepler ellipse in polar coordinates. It says that r1 squared is, what was it? A squared 1 minus epsilon squared divided by 1 plus epsilon cosine phi squared, right? This is r12 squared. Yeah, polar coordinate expression for an ellipse. And for phi dot, we had this expression which I'd used 20 minutes earlier or so already. I have phi dot squared, so I square it. Then I get g m1 plus m2 1 plus epsilon cosine phi r should. Yeah, I think it's true. It comes with a square in the expression for phi dot, so I have now a power 4, a to the 3, 1 minus epsilon squared to the 3. So this here is r12 squared, and this here is phi dot squared from earlier expressions. And the rest is just what it is. Okay, this can be a little bit simplified. So, I write it again. So I have m1 and 2 divided by 2 m1 plus m2 r12 dot squared. And here I have a squared divided by a cubed. Give 1a downstairs. This squared divided by cubed gives 1 minus epsilon squared downstairs. This here gives the bracket squared in the numerator. And the rest is g m1 plus m2. Bracket closed. Plus, no, it was a minus, right? Minus g m1 m2 over r12. Okay, and now I see that this here, without these terms, what is this term here? This can be expressed again in terms of r12. So this is what? r12 squared plus, I write this first, g m1 plus m2, and I write here r12 squared. That's not exactly what is written here. I have these two terms, I have them squared here, but they are not squared here, so I have to multiply this with 1 minus times 1 minus epsilon squared. Yeah, so this here is exactly this quotient. Minus g m1 m2 over R12. So that's the expression I wanted to derive. And now this changes over time, of course. This is a function of time, this is a function of time, this is a function of time. But the total energy is conserved. Now I'm back to the idea that there's no radiation going away. Yeah? I'm not talking about this adiabatic change of the energy. So if I just do ordinary classical mechanics without radiation, then this is a conserved quantity. So I can calculate it anywhere on the orbit. It always gives the same quantity. So in particular, I can calculate it at the, well, at the, with the sun, I would say at the perihelion or aphelion. Here one says upastron. Yeah, it's the moment where this connecting vector R12 has its maximal length. Yeah. If I had just the motion and the potential, then I would say from the center of the potential to the moving body in the upastron position, I have the maximal value. Here it's about the relative coordinate, so I have to say the relative coordinate takes its maximum value. Then of course R12 dot is 0, yeah, because it's the extremum, the maximum. And R12, well, what is the maximal distance of the boundary points of an ellipse from the center? This is the semi-major axis times 1 plus epsilon, right? For the periastron, it's 1 minus epsilon, and for the upastron, it is 1 plus epsilon. So E must be this expression where I insert these values. I can insert values at any point of the ellipse, but in particular this point, and then I get convenient values, convenient expressions. So this is 0. Then I have G, M1 plus M2, A, 1 minus epsilon squared. And this here squared is now A squared 1 plus epsilon squared. And the second term is G M1 M2 divided by A 1 plus epsilon. So I have here the same factor. I have here an A, here an A. And because I want to write everything on a common denominator, I multiply here with 1 plus epsilon. Then I have what? I take G M1 M2 divided by 2A 1 plus epsilon squared out of the bracket. Then what is left here is just 1 minus epsilon squared, right? And here I have this factor of 2 times this here. So I have plus 2 plus, no, there's a minus in front. I have minus 2 epsilon. Okay? This gives what? This gives minus, most terms have a minus sign, minus G M1 M2 over 2A 1 plus epsilon squared. And here I have a minus sign taken out, so I have plus 1 plus 2 epsilon plus epsilon squared. This is 1 plus epsilon squared by the binomial formula. So you see, the result is very nice. Epsilon drops out. So the energy of such a binary system, of such a two-body system, is determined by the masses and by the semi-major axis. The eccentricity drops out. It plays no role. Yeah? So you have circular orbits with these parameters, or you have elliptic orbits. Yeah? As long as the semi-major axis is the same and the masses are the same, you get the same energy. So the energy doesn't feel the eccentricity. The eccentricity is felt by some other quantity, namely by the angular momentum. Yeah? The angular momentum is strongly dependent on epsilon, but the energy is not. And now we can calculate how the energy changes. So we have this formula, minus dE by dt is our radiated power. I drop the arguments. We have to keep in mind that it's always to be taken at the retarded time. And what is this? Now we can calculate this time derivative. Yeah, the logic is a little bit subtle, and I say it again because when I started working with these things, I really had problems to understand this. Sometimes things are time independent, sometimes they are time dependent. Yeah. So when we speak about the motion with a fairly short period, yeah, then we treat the system as if all these parameters, A, epsilon, and so on, were time independent. And then we see, hey, this cannot be true. There's radiation going away, so they cannot be strictly be time dependent. And then one introduces the idea of these things being slowly time dependent, as one says, adiabatically changing. Yeah? And this is what I now want to calculate. Now I say, what I've calculated here, so the assumptions which I have made during this calculation cannot be strictly true. This A cannot be strictly constant. So I have to assume that it depends slowly on time, that it depends adiabatically on time. And now I calculate from this formula this time dependence. Of course, you might say, why not say M1 and M2? But, well, we are talking about Newtonian bodies, yeah? So, yeah, not some kind of nuclear fusion or nuclear fission or something like that, where really rest masses are transformed into other forms of energy. So for such a mechanical system, yeah, the only way in which the energy could change would be a change of the A, right? So we assume that these things remain constant, but that this changes slowly in the course of time, and we can calculate how it changes. So minus the E by dt, is G, just a second, let me just write this down then, 2a squared dA by dt. Minus, wait a minute, minus, there's another minus. That's the left-hand side. Yes?
But is it a mathematically rigorous approach to consider?
Okay. Question was if what we are doing here is mathematically rigorous. Yes, I think it is. You just have to fix the time scales on which certain statements are true. Yeah. So as long as the motion, here's a frequency involved. So we will specify in a minute to circular motion, then we really have a constant frequency, yeah, a frequency omega. And if now the time scale on which the observation at a large distance is done, if this is big in comparison to the period associated with this omega, then this is a mathematically rigorous thing. Because then the averaging is satisfied, yeah? The period which you are considering contains really many periods. Yeah, so it's allowed to average this out over these periods. Of course, if you wanted to know the radiated energy, the time change in the radiated energy on the same time scale as the motion takes place, then this averaging procedure would of course be nonsense. Yeah, so this wouldn't work. But as long as the periods of the motion are small enough, so that I have really many cycles to average over, then this is okay. Then this is a reasonable thing. Okay, this was the left-hand side. And the right-hand side, let me check the sign. Is the sign correct? E. There's a minus sign here. E is negative. This makes a plus. And from the derivatives, there comes another minus. Yes, it's true. So P should be positive. Because A should be decreasing, right? Let me see. Is P positive? Of course, P is positive. Yes. Good. I think at least the signs are correct. So here is a P. So P is 32 over 5 G to the 4 M1 squared M2 squared M1 plus M2. 5 I have already, but C to the 5 A to the 5, 1 minus epsilon squared, 7/2. So that's the formula which tells me how the A is changing. Can be a little bit simplified. You have an A squared, then this becomes an A cubed. I have M1 and M2 on both sides. I have a G on both sides. Anything else? No, I think not. So maybe I write it in this form that I write this A to the other side. Then I have A cubed dA by dt is what? Then it is minus 2 this here. Minus 64. Wasn't that a 15? Oops, let me see. Is that true? I had to, wait a minute. It was 96 divided by 15, and then I had divided numerator and denominator by 3. Yes, I think it's true. 5, yeah, there comes only this 2 to the other side, and everything else is as it was. 1 and 2. Oh, I forgot the epsilon terms. 1 plus 73 over 24 epsilon squared plus 37 over 96 epsilon to the 4. C to the 5, 8. Oh, no, I took this to the other side. 1 minus epsilon squared 7/2 and the curly bracket. That's it. This formula tells us how the semi-major axis changes. Well, actually it would tell us how the semi-major axis changes if we knew how the eccentricity changes. Yeah? Also the eccentricity will become adiabatically time dependent, and unfortunately with the formulas we have at our disposal we cannot derive the time dependence of the epsilon. So this formula is not fully useful because we don't know the time dependence of the epsilon. How do we get the time dependence of the epsilon? Has anybody an idea what you would have to do in order to find this out? So we have here calculated, it was a long calculation, yeah? The used result, which we had derived already 2 weeks earlier, or even more early. We had derived the radiated power, energy change, yeah? Change of energy over time. And we have seen that this only gives us the change of the semi-major axis, not of the epsilon. What else could one do in order to find the change of the epsilon? Anybody an idea?
Maybe look at the
Yes.
conservation of
The other conservation law, yes. Angular momentum.
yes.
Angular momentum, that's it. So one would have to calculate also the analogous equation for dl by dt. Yeah? And this is even more complicated than this. It was also done by Peters, yeah? In a second paper. This first paper is already complicated enough. The second paper is even more complicated. And I will not do this here on the board, definitely not. What we need is this energy momentum pseudo-tensor. We need really all components of them. I had calculated only the mixed components, which was sufficient for the energy flux. But for the angular momentum, you need all the other components. So you would have to go back and to calculate all this in more detail. And the expressions are considerably more complicated than for the energy. Probably you agree that this was complicated enough, but for the angular momentum it's even more complicated. I will tell you just the result, which was in this paper by Peters from '64 for dl by dt. And then we will use this in one of the worksheets for calculating the dependence of epsilon on t. I think I can squeeze this here. Or maybe here. An analogous, but even more tedious. Gives dl by dt. Let me also write it with a minus sign. 32 m1 squared m2 squared g to the 7/2 m1 plus m2 1/2 divided by 5 c to the 5 a to the 7/2 1 minus epsilon squared times 1 plus 7/8 epsilon squared. Oops, that's it. And this implies a formula for the epsilon by dt. And we will derive this. We will assume that this is true. Yeah? This is awfully complicated to derive this. I will not derive it on the board and not type it out. Let's just believe this. You can look it up in this paper by Peters if you want to see the proof. But when we assume this formula, then it's comparatively easy to get an equation for the time dependence of epsilon. And we will do this on worksheet 5. And then we have a coupled system. Oops, no, this one. We have a coupled system for a as a function of t and epsilon as a function of t. And this is well determined. Yeah, so this has unique solutions if the initial conditions have been given. And this equation has the interesting feature that if you give as an initial condition epsilon equals 0, so you start with a circular orbit, then the orbit remains circular. Yeah? That's important because it allows us to specify this equation to circular orbits. Yeah? If an orbit would become eccentric in the course of time, this would not be a reasonable assumption. Yeah? But as we can check from this formula when we have it, circular orbits remain circular, so we can assume that we can apply this formula to circular orbits, and that's what I want to do in the rest of this lecture. And this will give us the opportunity to discuss the physics of these systems any further. We have seen, I've emphasized this already, that for orders of magnitude, the epsilon is not very important. Yeah? When we had looked at this expression here, we had seen that in essence, what gives the order of magnitude of the effect are the masses and the A. Yeah? And for this reason, considering circular orbits is quite instructive and gives a good idea. Anybody tell me how much time you have? Half an hour? Okay, very good. Yeah, then I think I managed to do everything that I wanted to do today. So we will now specify these formulas to which one do we need? The formula for the A. I should not erase this. Oops. We will specify this to circular orbits and discuss this a little bit further. The Hals-Taylor pulsar is not circular. It has a considerable eccentricity. But as I said, if it's just the goal to get an idea about the order of magnitudes, then the eccentricity has not a big effect. I think it's 0.6 or something like that, the eccentricity. Oops. Oops. So let's consider circular orbits now. For the rest of this lecture, orbits. So this means epsilon is equal to 0. Yeah, this means circular. It does not necessarily mean that the masses are equal. Yeah, the masses may be unequal. So if I have one mass here, the other mass here, the center of mass is not necessarily in the middle of the two. It may be here, for instance. Yeah? So here is the origin of our coordinate system. And this was a vector which I had denoted R1, position vector of one of the two masses. This is the position vector of the other mass. This is R12. Yeah, the vector from here to here is R12. And this is the angle phi. And now for a circular orbit, we have phi dot. If we specify this expression, which we had several times on the board, if we specify this for epsilon equals 0, we see that it becomes time independent. So this means that if I have a circular orbit, well, you know this, then the motion is harmonic, yeah, with a constant frequency. This is a special case of Kepler's second law, of course. Where was phi dot here? Here. If I specify this to the case epsilon equals 0, I have just root g m1, m2. Here was a term with epsilon, and here was here's a to the 3/2 and the term with epsilon. So this is constant now, apart from the adiabatic change. Yeah, and so I will denote this by omega. So I have now a constant frequency with which the whole system goes around. Yeah, so this rotates now rigidly. Yeah, this rotates rigidly about this point with constant frequency phi. That's the case we want to consider. And our differential equation for A, it was what? We still have it on the board. The equation which gives us the adiabatic change of the A here. Can you see this? Oops. This equation here. If I set epsilon equal to 0, then it simplifies. So I have minus 64 over 5 g cubed m1, m2 m1 times m2 m1 plus m2. And here I have c to the 5. Oops. A is now this constant distance, yeah? This is A. Oops. And everything else is just 1, yeah, because epsilon is 0. So this is a constant, which I denote A. Or let me denote it 4A. Because then I have 1 over 4 a cubed dA by dt minus a is this here. And this is, by the chain rule, just dA to the 4 divided by t. And because a is a constant, this is not very difficult to integrate this. Yeah? So this gives us a to the 4 is an integration constant, which I call a naught to the 4, minus at. Okay? That's the solution to this very complicated differential equation. And well, this can be written in a nicer form in this way. Minus do I want to have the 4? Let me check just that to make sure that the notation is consistent with my notes. I have yeah, this is of course nonsense what I've written here. That's of course nonsense. Oops. I think what I meant was this here. Could this be true? Yeah, I think that looks better. If I differentiate this, then I get the 4 down. I get an a cubed and then the a by dt. Yes, I think that's what I meant. And then I have the 4 here, right? Then I have the 4 here. And in my notes, I also have the 4 there. So this is now an agreement. Then I have 1 minus 4at over a naught 4. So if I take the 4th root, I get a as a function of t is a constant a naught, some integration constant, and then 1 minus, well, this must be dimensionless, so this factor, a naught to the 4 divided by 4a, must be a time. So I call it TSP, SP for spiral. This in spiral time, TSP, is just a naught to the 4 divided by 4a. So you see, in this model, what we are entertaining here, which is in a sense, of course, over-idealized, in this model, a of t becomes 0 at a finite time, TSP. Yeah, at this time, the two things have come together at the end of a spiral motion. That's, of course, an artifact of our approximation. that we assume that we have point particles which move according to Newtonian mechanics. Yeah? Of course, if the A has become very small, then this approximation breaks down. There comes a point where we have to stop our calculation because our approximation is no longer justified. But nonetheless, this TSP gives a good idea about the lifetime of the system, just about the order of magnitude. Because if we start with a big radius, with a radius which is big in comparison to the Schwarzschild radii, this A of t will be more or less constant over a very, very long period. Typically, if you insert masses like that for the Hals-Taylor pulsar, you get in-spiral times of millions of years. Yeah, millions of years. I think 600 million of years it is for the Hals-Taylor pulsar. We will calculate this. So it's only at the very end of this process, within, I don't know, minutes or something like that, we have really strong gravitational effects where this approximation breaks down. This approximation that we have mass points which approach each other in a spiral motion. So for the order of magnitude of the lifetime, that's a reasonable approximation. From the formula for A of t, of course we get a formula for T of t with Kepler's third law. So this was, what was it? T is 2 pi a to the 3/2 divided by root g m1 plus m2, right? And we can insert our expression for A of t. This gives 2 pi a naught to the 3/2 divided by root g m1 plus m2. And then I take, I have to raise this to the power 3/2. 3/2 times 1 over 4 is 3 over 8, right? 1 minus t TSP 3 over 8. Yeah, I already said that funny factors occur in this kind of calculation. So this is the way in which the period depends on time. Yeah? And you see also the period, of course, becomes 0 when t approaches TSP in this approximation. What one very often considers, and what is also very often plotted, is a time derivative of this. This is a dimensionless quantity, right? Capital T is a time. If I differentiate it with respect to t, I get something which is dimensionless. Let me write this down. This is what? 3/2 root g m1 plus m2. If I differentiate this, I get a factor 3/8. 1 minus t TSP. 3 over 8 minus 8 over 8 is minus 5 over 8. And the internal derivative gives a minus TSP. So in essence, this goes with this factor. That's the time dependence. And if you plot this, that's a plot everybody has seen before, I'm sure. If you plot this, so if you plot dt of t by dt over time. So we see it is negative. I should have drawn the axis a bit higher. Oops. So it starts with some negative value. Yeah, there's this value here. That's at t equals 0. This negative value. And then it goes down like that. Yeah. And in our approximation, it asymptotically approaches minus infinity here. So it does something like that. Of course, the final phase is not realistic. Here we cannot use our approximation for this, but for this entire branch, it's a very good approximation. And I think you have seen this graph. That has been confirmed by the Hals-Taylor pulsar with incredible accuracy. Yeah? I will show you the original diagrams from the papers by Hals and Taylor, and by Taylor and Weisberg in particular. Weisberg was a theorist who evaluated the Hals-Taylor pulsar. Some people say it was not quite fair that he did not get the Nobel Prize. Yeah? He did all the theoretical calculations. The Nobel Prize was awarded to Hals and to Taylor. Hals, a PhD student who did the observations, and Taylor, his thesis advisor, who played, of course, also a major role in the evaluation of the whole thing. Okay, so this is with our oversimplified model, Newtonian mass points which spiral towards each other, we can already reproduce this curve, and it is reliable up to the very, very last phase. So this is d capital T by d lowercase t. That's what is always plotted. You can also consider the period, omega. That's also something which is often done. So omega of t, this is 2 pi divided by t of t. Yeah, it's a time-dependent period. Well, we can write it down from the expression which we have on the board. So I have to invert this and then cancel the 2 pi. So this is root g m1 plus m2. I should have looked to this expression divided by a naught 3/2. And I have the inverse of this, so it's minus 3/8. 1 minus t tsp. What was it? Minus 3/8. And what people often consider is a so-called chirp. This is a time derivative. I had written it in this form. Yeah, this is something, a terminology which is used not only in connection with gravitational waves. Of course, it comes from sound waves. Yeah, if you have a sound wave where the frequency changes, and let's assume this quantity is positive, omega is positive, this means the frequency becomes bigger in the course of time. This means the pitch becomes higher. Yeah? And this is what in English one calls a chirp. Yeah, it's a sound a bird is producing, zwitschern in German. So if a sound goes up. So this quantity is often called a chirp if you are dealing with time-dependent phenomena where the frequency changes over time. And we can calculate the chirp from this expression easily. Root g m1 plus m2 divided by a naught 3/2. So I have to differentiate this now. This gives minus 3/8. Inner derivative gives another minus tsp 1 minus t tsp minus 3 minus 8 is minus 11, right? Okay, we can discuss all this a little bit more specifically because for circular orbits we can actually write down the field in the far zone explicitly, and that will be the last thing I'll do today. So we had the quadrupole tensor. So for circular orbits, the quantity which we had denoted I1, which for non-circular orbits depended in a fairly complicated way on time, is actually time independent. For circular orbits, it is just m1, m2, a squared, m1 plus m2. And this means that the quadrupole tensor, written as a matrix, we had this expression on the board. It was I1/2 times 1 plus cosine phi, sine phi 0, sine phi 1 minus cosine phi, cosine 2 phi, sorry, cosine 2 phi, everywhere 2 phi. 0, 0, 0, 0. This becomes very simple because 2 phi is, in our case, just 2 omega t, where omega is a constant. It changes adiabatically, but for the periodic process, it's treated as a constant. So we can easily differentiate this, and this is a constant, so we have no problem with differentiating this. So what was so awfully complicated, just involved in the case of elliptic orbits, now becomes almost trivial. So we can immediately write down the first derivative and then the second derivative, which we need for the far field, 1/2. Well, if I differentiate this, I get a factor 2 omega. And then I have cosine gives minus sine 2 omega t. Sine gives plus cosine 2 omega t 0. Cosine 2 omega t, and this gives a plus sine 2 omega t. And the second derivative gives us the field in the far zone. And this can be explicitly written down. So gamma KL, we want to know it at time t and at position vector r. This was the second derivative, so we have to differentiate this another time. And the prefactor was what? 2g over c4r. R is the modulus of this vector r, where the observer is sitting. Yeah? Okay, and then times this differentiated gives another 2 omega. So I have 2 omega squared I1. And then this differentiated. This gives minus cosine 2 omega t minus sine, retarded time. Omega t minus 2 omega t t omega r over c. Minus 2 omega r over c. 0. Here we have minus sine 2 omega t minus 2 omega r over c. And the derivative of sine gives plus cosine 2 omega r over c. 0, 0, 0. Okay. So you see the frequency of the wave is 2 omega. Yeah? This has something to do with the fact that we have a quadrupole wave. And actually, if you remember the examples which we have done in the last worksheet, it was always this way. You have a source which has a certain periodicity omega, and the gravitational wave has a periodicity 2 omega. That's the reason why I use a capital omega for the period of the source, because I use little omega for the period of the gravitational wave. Now, can we really interpret this if I look at this consider as a sufficiently small domain of space-time? Can I really consider this as a plane harmonic wave in the way we have treated it mathematically? No, not directly, because it's not on the TT gauge. Yeah? But there's one particular point where it is in the TT gauge, namely when I am so my binary system is moving in the x1, x2 plane when the observer is looking precisely from the top. When the observer is at the 3-axis, you see, the 3-axis, then I have transversality, and I have also vanishing trace. Yeah? So for observer, at r equal r times n, that's a unit vector, where this is this unit vector. And we read from this expression that then we have gamma KL is the same as gamma KL transverse traceless. Yeah, for other positions of the observer, that's not true. Then you would have to project this, which is always a bit cumbrous. So for this reason, I will now only consider the case that I'm watching directly from the top. I'm looking onto my binary system from the top, and then I can write down the wave quite explicitly, and I can discuss how the gravitational wave signal that arrives at the observer, how that looks. So for the observer at this position, we can use what we have learned about plane harmonic waves when we did this, I don't know, 4 weeks ago or so, when we assumed that we were in the TT gauge. I hope everybody remembers that we had decomposed the gravitational wave into a plus mode and a cross mode. And we can easily recognize the plus mode and the cross mode for the signal that comes from our binary. So, yeah, we see here I have the cosine terms. The cosine terms have in the 1, 1 component and in the 2, 2 component the same value with different signs. That's precisely what we had for a plus mode. And here in the 1, 2 component and the 2, 1 component, we have the two things. This is what gives us a cross mode. Yeah? So we have a plus mode. We can read it directly from this expression. For the observer at this particular position, it only works for the observer. We can apply this formula directly only for this particular case. So there's a prefactor. What is it? 4g, 4g omega squared. 4g omega squared I1. Of course, falls off is 1 over r, c to the 4r. And then I have what? Then I have, let me write a minus sign in front of it because we had the A11 distinguished as the A plus. So I have a plus 1 here, a minus 1 here, 0, 0, 0, 0, 0, 0, 0. And then I have cosine 2 omega t minus 2 omega r over c. And the cross mode is the one with the same amplitude. Then I have here the ones. Here and here I have the ones, and everywhere else zeros. And instead of the cosine, I have now the sine. The sine, but I can rewrite this with the help of a phase factor. Is it plus or minus pi half? The sine is the cosine. Oh my goodness! The sine is the cosine minus pi half, right? So you see the two things are not in phase. That's usually the case. And, but they have the same amplitude. At least for this particular case, they have the same amplitude. Here you see, if you superimpose these two things, if you take the sum of the two things, then you get the right-hand side of this equation. Yeah? So the total gravitational wave which arrives at the observer is a sum of the plus mode and of the cross mode. And now, the crucial thing is that this omega here is not strictly constant. Yeah, it is adiabatically changing in time. And the last thing I want to, here, maybe I should write this. If you compare this with the formulas we had for the plane harmonic waves, the little omega, which we had in the earlier lectures, corresponds to 2 times the big omega. And the wave vector k is 2 omega over c, and it points in the direction where the observer is sitting, yeah, in the vertical upwards direction. And the signal depends on time according to, for both modes. Yeah, both modes have the same time dependent up to a phase factor. Depends on time according to, let me call this h of t. Yeah, where's the time dependence? Here's omega squared. And omega is now adiabatically time dependent. Cosine 2 omega of t times t plus a phase, which is not time dependent. And omega t is, do I have it on the board? Yes, up there. That's the omega t, with omega t as we have calculated it up there. Let me write it again. Root g m1 plus m2 divided by a naught. That's the initial condition for the radius. 1 minus t divided by t spiral to the power what? Minus 3/8. Yeah? And if you plot this as a function of t, then you see, it becomes singular when t approaches t spiral. Yeah, it becomes singular. And it becomes more and more oscillatory because this factor becomes singular. So what you get is what is called a chirp. Actually, I produced this with Mathematica, and I was really pleased that it looks precisely as I wanted to look at. So here is somewhere the limit. So it starts oscillating, then the period becomes smaller, and the amplitude becomes bigger. Yeah, and this approaches this then in a limit. In this mathematical idealization, it really goes to infinity. Yes, it's a typical chirp signal. Of course, the final phase is unrealistic. But up to, I don't know, a certain point, up to a certain increase in the signal strength, it is quite realistic for a merger of a two-body system. So this is the simplest kind of a waveform which you can theoretically derive. This is just a waveform for two mass points on circular orbits which spiral into each other. That's how the signal looks. Probably you know that the signal which was observed by the LIGO detectors was not precisely this. Well, actually, up to here, it is very similar to this. Yeah? It looks more or less exactly as this formula prescribes. But then, of course, there's not this infinite increase. There's rather what is called the ring down. Yeah? Then the two black holes merge. They form a single black hole. There's no singularity. And then it settles down in a new stationary state. So instead of this increase, I get a ring down. That's the difference. But the in-spiral phase is not so badly described by this very simple model. And of course, this kind of waveforms has been calculated for many, many much more complicated situations. That's the simplest waveform you can imagine. Two point particles spiral towards each other. You can do it for not just Newtonian, taking post-Newtonian terms into account, approaching the full general relativistic theory by a kind of approximation procedure, which is called post-Newtonian approximation. You can take spins into account. You can consider the case that the two bodies have a spin. And where the waveforms always reflect these, at least some of these features. And the art, what these data analysts have to do is, when they see a signal, then they have to find in their big data bank of waveforms, they have to find the one which fits this best. And then they can read off the parameters and see what kind of system they have found. So what I am able to show you here is only this very simple, oversimplified example of two Newtonian mass points spiraling into each other. And for that, the waveform is very simple. It can easily be reproduced. And I really encourage you to do this with Mathematica or Maple or whatever you prefer, and to see how a signal of this kind behave, to get an idea where this particular shape comes from. Okay, in the next lecture we will then link up with observations. So I will then discuss the Hals-Taylor pulsar in some detail, the real observations which have been done, and to what extent this simple model fits to the observation with the Hals-Taylor pulsar and also with other binary pulsars. By now we have a couple of other ones, even better ones than the Hals-Taylor pulsar. So we now have really a lot of things with which our calculations can be compared. Okay. And on Friday we have 90 minutes lectures, yeah? Because last week we didn't have a second lecture. Okay, see you on Friday.